Hello, and welcome to a brand new section of this course, High Performance and Parallel Computing. Here, the first video deals with accelerating Python code with Numba. When it's too difficult or impossible to vectorize an algorithm, you often need to use Python loops. However, Python loops are slow. Fortunately, Numba provides a just-in-time or JIT compiler that can compile pure Python code straight to machine code thanks to the LLVM compiler architecture. This can result in massive speedups. In this video, we'll see how to use Numba to accelerate a mathematical modeling simulation. To install Numba, just type conda install Numba on the command line. It may take a few seconds. It will ask you if you want to proceed, so we say yes. Done. Now go to Jupyter Notebook, and here I've already pasted all the codes required. I will explain each part one by one. So we first import a few packages. We will simulate a random walk with jumps. A particle is on the real line, starting at 0. At every step, the particle makes a step to the right or to the left. If the particle crosses a threshold, it is reset at its initial position. This type of stochastic model is notably used in neuroscience. Without the threshold, this model is called a Brownian motion. Although a Brownian motion can be efficiently simulated in NumPy with np.comSum, a stochastic model with a threshold and jumps requires a loop. This random function returns a random -1 or +1 value. Let's write the simulation in pure Python. The function walk takes a number of steps as input. At every step, the function adds a random step to the previous position in order to get the new position. An if statement implements the threshold and jump. Let's run this function with n equals 100,000. And we pass n as an argument to the walk function. Following that, we run the plot method. And here's the output with the trajectory. How long did it take to simulate this trajectory? Let's find this with the timeIt magic command. As you can see, it took around 84.6 milliseconds for execution. Now, let's JIT compile this function with Numba. Here, we have defined a step Numba function. The second function is the walk Numba function. All we had to do was to add a JIT decorator on top of the two functions. The body of the functions remain the same between the pure Python and the Numba versions, except that we call step Numba instead of step in the main function. We'll explain the no Python equals true argument shortly. After this, we evaluate the performance of this compiled function, and we can now see the time taken by the walk Numba function. This is a 30 times speed improvement. IPython tells us that the first call was much slower. This is because the function was compiled on the fly the first time we called it. Hence, Numba is the most effective when a given function needs to be called many times. The no Python equals to true argument is not strictly necessary. Numba can compile a Python function in two modes, Python mode and no Python mode. In Python mode, the compiled code relies on the CPython interpreter. In no Python mode, however, the code is compiled to standalone machine code that doesn't rely on CPython. The no Python equals to true argument is not strictly necessary. Numba can compile a Python function in two modes, Python mode and no Python mode. In Python mode, the compiled code relies on the CPython interpreter. In no Python mode, however, the code is compiled to standalone machine code that doesn't rely on CPython. Numba needs to know the exact types of the function's parameters, return values, and internal variables. It uses type inference to find out the types automatically when possible, but you can also specify the input and output types explicitly. You'll find more details in the documentation with the Numba main page at numba.pydata.org. Python features supported in no Python mode can be found at this website. And you can learn more about NumPy features supported in no Python mode at this page. Numba also supports the creation of NumPy universal functions, ufuncs, with the @Vectorize decorator. This feature lets you turn a Python function implementing a mathematical scalar operation into a vectorized function that works on NumPy arrays on an element-wise basis. Here is an example. We want to compute a complex mathematical expression on a NumPy array. The standard way of doing it with NumPy is inefficient because many array copies are silently performed during the temporary steps. Let's execute this code. And here's the output. So we can use the Vectorize decorator to define a new universal function. Following this, we use the kernel function. And next, we use the timeItMagic command with kernel function to be applied on a NumPy array. As you can observe, this function is about twice as fast as the standard NumPy version because temporary array copies are avoided. It is possible to make this computation even faster by taking advantage of multi-core processors and graphics processing units, GPUs. Let's illustrate this by using another package called numexpr, which is similar but older than Numba. It can be installed with conda install numexpr. Let's run this. It may take some time. Done. As you can see, it says that the requested packages are already installed on my machine. Now, let's get back to the Jupyter Notebook. Here, the evaluate function takes a string as input, which is slightly less convenient than Numba's decorators. However, it uses all available cores by default, which explains why it is several times faster than Numba here. And here's the output giving us the exact time taken by the function for execution. Let me share a few good-to-read references. So for universal functions with Numba, you can read at numba.pydata.org. And you can find the numexpr documentation at this website. That's all for this video.